Hello. Hello, can you hear me?
Yes, ma'am.
Okay. So I have uploaded whatever materials I have for the rest of the things, and more or less I've completed all information update in the classroom. I hope you have seen them. Hello, please respond. Have you seen them? Okay. Shoptoshi said yes, ma'am. So, is it? I mean, did you go through that decision tree? That it's a handwritten notes that I have uploaded. Okay, Shoptoshi only said yes. Fine. Thank you.
হ্যালো ম্যাম,
হ্যাঁ।
সপ্তর্ষিকে ঢোকাতে বলছে ক্লাসে। ও অন্য মেলদের জয়েন করছে ওই জন্য।
ও সবাই তো জয়েন করে গেছে, আর তো দেখাচ্ছে না কিছু।
ওকে ওকে।
আর তো কোথাও নেই, কিছু অ্যাডমিট করার জন্য বলছে না কেন। ওকে। So can you see the screen?
ইয়েস ম্যাম।
Yes. Okay. So I'm just quickly going through whatever is left over for this topic. As I said, most of them you have done it earlier. So I'm just quickly going through it. So last time we saw what was called this decision tree. So, and I asked you to do this entire decision tree. So in this, note, actually the entire thing has been done for the sample, the data set that was used. Okay. So you can do it on your own and just see if you are getting the same result. So that will help you to in exams, like if you how to do it. Just knowing the algorithm is not enough, you need to do it properly. So this information gain measure was used for selecting an attribute in building the decision tree, and that algorithm is typically called this ID3 algorithm. Okay. Now, so there are some problems with this ID3 algorithm. Like the problem is like uh, this information gain measure. It's somewhat biased towards test sets with many outcomes, meaning that if instead of yes no there are too many kind of outcomes, I mean too many categories, too many classes, then it is biased towards such a kind of thing. So what happens in those cases, it prefers to select attributes that has large number of values, this ID3, using this information gain measure. So that's why in order to balance that biasing thing, another selection attribute is used, which is called gain ratio. So I'm not covering that, but this gain ratio um, attribute selection measure, this gain ratio selection measure is used in another version of decision tree algorithm, which is called this C4.5. So that you maybe you have seen those algorithms in your earlier class, maybe, I don't know. Okay, just 1 second. So that is called, so C4.5. So this is actually a successor of this ID3 algorithm. Okay, and which uses a metric selection, attribute selection metric, which is called gain ratio. So I'm not going into all that detail, but in brief, this gain ratio is some kind of it tries to overcomes the bias that is there in ID3 algorithm, and it actually uses what is kind of normalization. It uses normalization to that information gain that we have used in our ID3 algorithm. Okay. So it's basically a normalization on the information gain, and by this it is able to overcome this bias when there are too many different outcomes in the data set for a particular attribute. So next we will move on to this Gini index. So this Gini index is used in what is known as this typical your CART algorithm, right? So classification and regression tree, that is the full form of this CART. So what is this Gini index is about? So here again we are using the same setup that we have used earlier. So D is your training set with the size this D, and C is the different types of classes C1 to CK, and A are the set of attributes A1 up till AM. So now Gini index, that is defined like this: G for that entire data set D is 1 minus summation of pi square. Summation I is equal to 1 to k. Remember that k is the total number of classes that you have. So, and what is pi? Pi is probability of a tuple in this D belonging to class Ci. So this I represents a class I. Okay. So in other words, this pi can be represented like this: for a attribute D, which class it belongs to. So the number of tuples in D with class Ci, and divided by the cardinality of this of the data set D. So now what it essentially means is it measures a kind of impurity of data set. Okay, so that means impurity in the sense that in a particular thing, I want to make it like everything should belong to a kind of same class. So if some other class is in there, so that is what is kind of impurity that we are talking about. Okay. So now the smallest value of this G of D, that is the Gini index, it can be 0. So that means all have the same class, no impurity. So that is what is the meaning of impurity. And largest value of GD, what it can be? 1 minus 1 by k. So that means what it means is, it means that you have so same number of tuples for every class. So that means that it is the classes are evenly distributed between the tuples. So that means, that is what I was saying, that frequency of each class is nothing but 1 by k. Okay. So this is the two extremes that it can happen. 0 means everything is pure in that particular set, no impurity. and the other possibility is that everything is very well distributed. So, Gini index is associated with the diversity. Okay. So, suppose a binary partition on A splits D into. Um, so, essentially, with this Gini index also, we are doing partitioning. So, binary partitioning we are doing. So, suppose a binary partition on A splits this D into two sets, D1 and D2. Then what we take is the weighted average Gini index of splitting, and that is denoted by on attribute A, Gini index on D. So, since it is a weighted average, so it is the number of elements in D1 divided by the total number of D and Gini index of D1. Okay, and similarly for D2 also it is exactly the same, and since it is a weighted average, so this is for one partition and this part is for the another partition. So, so this binary partition of this D will reduce the impurity, and the reduction in impurity, how we are measured. So actually we want to reduce the impurity as we go along building the decision tree. Okay, so that's why you need to, just like information gain, where we are always increasing, maximizing the information gain. And here we want to reduce the impurity. So we want to like kind of minimize the impurity. Okay, so and how do you compute that reduction in impurity? So that is using this, like we are using a function, let's say gamma. So this is A comma D. A is the attribute and D is the in the previous node. So in the hierarchy, it is the parent of A. So G of D minus G of D with respect to the attribute A. So this is what is called the Gini index of diversity. Okay, so in impurity or attribute with minimum value of G of D is selected. So that is what I was saying. We want to minimize the impurity. So that's why we choose an attribute which has the minimum value of this GA of D. That one is selected for the attribute to be splitted. Okay, so that means the attribute that maximizes the reduction. So for example, let's look at this example. So essentially what we will be calculating is this, GA of D. So let's say it's again a very small example where, so these are the attributes, like whether a person loves popcorn, loves soda, what is his age, his or her age, and whether he loves a particular film. Okay, so this is our actually target variable or y. Okay, and these are the x's. So these are the x's. So you see that in everywhere it is only yes, no, loves popcorn, yes, no, loves soda, yes, no, loves a film, that is also yes, no, and age is a numeric or discrete values. Okay. So now how do you do that? So let's say I choose this loves popcorn. So there we have this true side and false side. Okay, so I mean true side, false side in the sense like two branches. So now if you look at that, so in popcorn, so loves popcorn, yes. So 1, 2, 3, 4. Okay, so there are 4 yes part, and among them, look at this loves film or not. So among them you see this is no, this is no, this is yes, and this is no. So that means 3 no's are there and 1 yes is there. So 3 no's are there and 1 yes is there, right? So if he does not love popcorn, he or she, so then what is the situation? So this you have to look at this no, no, no. So altogether there are 3 no's. So if you add this, you will get 3. And among these no's, okay, let's do it this way, then it's easy to see. Among this no, there are 2 yes and 1 no. Right. So I've made this so that it becomes a little easy to see. So even for soda, we can do this thing. Love soda, does not love soda. Okay, so love soda. So there are how many yes? 1, 2, 3, 4. So here you see 3 plus 1, 4. Among these 4 yes, here you have 1. Okay, let me take another color. So this yes, this yes, this yes, this yes. So 1, 2, 3, 4 yes. 4 yes are there. So among all these yeses, how many no's? This one is no. Yes, so only 1 no. So that's what you see, 3 yes and 1 no. Okay. So similarly, where does not love soda, so that is this no and this no, this no. So there are 3 elements. So for every n, it is no, no, and no. So that is why yes is 0, all are n. So now you look at this. So this is a kind of reached a conclusion with no impurity. Okay, so there is no yes over here. So this is a pure class. There is no impurity. Okay, so this was the meaning of impurity in that respect. So now I compute what is the Gini impurity for a popcorn. Okay, so this is at the leaf level. So this for this true part of it. So what it is going to be, so if you remember this previous formula over here, it is 1 minus, so G of D is going to be 1 minus summation Pi square, and for every classes. So if you apply that, so it is, yes. So for this popcorn, what you see is, okay, let me just, yes. So 1 minus, then this part is in the summation after taking the bracket out. So that's why it has become minus. So probability of yes square or probability of no square. Okay. So in the popcorn side. So this one. So probability of yes square is 1 divided by 4. Probability of no is 3 divided by 4. Right. So that is what is written over here. And so it came out to be this 0.375. So this is the true part you have calculated. Then Gini impurity of popcorn with respect to false you have to calculate. So that means it is to the other side, this part. So similarly you can calculate that. You see 1 minus, then this side it is, this one is 2 out of 3 and this one is 1 out of 3. And you have to take the square of it. So that is what? 2 out of 3 square minus 1 out of 3 square. So we are getting this value. So if you remember that, so so next what we will do, remember that we have to then compute the weighted Gini index. So Gini impurity then is calculated as, if you remember that for every class, it was for every class there are 2 class, so that's why we have 2 compartment, I mean 2 component. So one Gini index we got 0.375. This is for the yes part and this is for the no part of popcorn. Okay. So, and this is what is the weight. So weight was what? If you remember what was weight, it is this D1 divided by D and here D2 divided by D. So if you look at that, what was D1? D1 was 4 in this case. So it is 4 and altogether 7 elements are there. I mean 7 entries are there. So 4 plus 3. So denominator will be the same for both the things. Only upper part is going to be different. And for the no part, there are 3 no's. If you see here, 3 no's. Okay. Yes. So 3 no's. No, not here. Here. 1, 2, 3. 3 no's and 4 yes. Right. So that is why it is like this. Okay, and so you get, finally you get this Gini impurity to be this 0.405. Okay. So now So if you calculate same way for this soda, so you will get this 0.214. So we want to reduce the Gini impurity. So this is obvious that for soda I will get lesser value of impurity, because we see when we have divided it here, there is one portion where we have reached a situation where there is no impurity, right? So that's why in this case this 0.214 is chosen as the selection attribute. Fine. Okay. So the next we have another thing, we have to select the attribute, right? So we have done popcorn, we have done soda. Now for age, how do you do it? For age, it is a discrete numerical value. So for that, how do you compute the Gini impurity? So typically one method could be this, that we sort the values since we have a numeric data. Okay, so 7, 12, 8, 35, 38, 50 and 83. Okay, so then I mean for consecutive things we find out an average. Okay, so average the adjacent one. So 7 and 12 average is this, 12 and 18 average is 15, 18 and 30. I mean continuously you do this averaging. Okay, so now what is required now is we need to compute the Gini impurity for each of these values. Which values? 9.5, 15, 26.5, 36.5, 44 and 66.5. Okay. So what we are going to, how our node is going to be, age less than 9.5, true and false. Similarly, age less than 15, true or false. Age less than 26.5, true or false. So 3, 4, 5, 6 things you have to do in this fashion. Okay. So for example, I have done one here. So age less than 9.5. So if you just see yes and no, so here you see that we have got a pure class and here we have got a non-pure class. Okay. So the impurity can be calculated as 1 minus 0 by 1 square minus 1 by 1 square. Okay, so this is for the true part of it. Okay, so this is for the true part of it. Age less than 9.5. Less than 9.5. Okay, so same way we can calculate what is for this one. I have not done it, but okay, it is found that it is 0.5. You can do it and see quickly. Okay, so then you do the weighted average for this two part, and as a result we get this 0.429. Okay, now same way we have to compute all the weighted Gini impurity. So for 9.5 thing we have got this 0.429. So then for 15, again if I do age less than 15 and I draw the tree like that, so then I'll be getting this. So same way if you can compute for all of them. So I've just written down what is the value after computing the average, weighted average Gini index. Okay, so among them whatever is the lowest, choose that one. So lowest we take any impurity, one of them. So for 15 and 44 we are getting the same value. So you can choose any of one of them, either 15 or 44. Okay, so the Gini impurity you are getting is 0.343. So now among them again choose the minimum one. So 0.343 is one value, the other value is 0.214 and another one is 0.405, right? So 1, 2, 3. So what is the minimum one? Soda has the minimum value. So this has the minimum value among 0.405, 0.214 and among all of them, and among all these, which is 0.343, right? So choose attribute with the lowest Gini impurity, that is this love soda with this 0.214 value. So now, so this is going to be your first attribute in the decision tree. So now for this true and false, again you will be building that, and then accepting soda, use the other two attributes like popcorn and age on both sides, popcorn and age on both sides. Okay, and keep on growing the tree in the same fashion. Okay, So this is about the using the Gini index in order to build the decision tree. So you build the tree top down in this fashion, and once you have built the tree, so for a given new input, let's say if I give the input that uh, loves soda, but uh, does not love popcorn, and let's say age is some 35, then I want to find what is the class, yes or no, whether he wants to see the movie or not. Okay, so for that you simply follow the follow this decision tree. I mean, if you love soda, go to this side, and then from there whatever branching will be there, simply follow that, and ultimately will end up in a class. Okay, so this is how decision tree is made, and how a new data is used, how in order to predict a class for a new unobserved data, you simply traverse the decision tree by looking at the decisions at every node, and finally when you reach the leaf, you will get a pure class over there, and that is the class of that particular input. Okay, so this is how you classify in a decision tree. So yes, so now so there are actually this decision tree has certain problems. Okay, so by the way, like since we have seen more or less like 3 different algorithms, let me just kind of give a comparison of um, what happens what happens when. So so actually the different decision tree algorithms you can, okay, let me just write. So if you can, the decision tree algorithms differ on certain aspects. Okay, so decision trees differ on either in splitting criteria, okay, how you are splitting, which kind of attributes you are using, I mean, and that leading to the tree structure. Because if your splitting criteria is different, the tree structure is going to be different. Okay, so typically we have seen this ID3, then C4.5. Briefly, I have said, I haven't said much about it, and then this CART algorithm, right? So now, if you look at the split criteria now, the split criteria. Okay, maybe I'll write this split criteria. So then ID3 uses what is called info gain. So this C4.5 uses gain ratio, which is nothing but a normalization of information gain. And CART is what it uses, this Gini impurity. Okay. Now, if you look at how the splitting is done, so if you think about information gain, you see that it is, I mean, it's in both the cases, like depending on the values. So it is a multi-way. Okay. And this is also a multi-way split. Multi-way split in both the cases, ID3 and C4.5. For different types of classes, we are getting different. If there are 3 different types of like low, medium, high, so then we are getting 3 branches, right? So here it is typically this binary. The split type is binary. Kind of we ask questions and then true false kind of thing. Okay, so that is one difference. Then if you look at the data type, what kind of data type is handled? So obviously here you use categorical data. Here you can use categorical and also continuous data. Okay. And here also you can use categorical and continuous data. So we have seen how to use this continuous data for CART. In fact, this CAR, classification and regression. So that means this can also be used for regression analysis, right? So for prediction also you can use this decision tree, right? So continuous data also you can give. Okay. So then what about if there are missing values? How does it cater to that? So ID3 cannot handle missing value, but this can handle missing value and this also can handle missing value. So if you talk about regression, obviously I was talking about this regression. So this cannot be used for regression. This cannot be used for regression, but yes, this can handle regression. So then I'm not going into detail, but you can use some kind of pruning for improvement. Pruning of some of the branches, you can make the tree smaller using some of the pruning techniques. So maybe you have learned them in your machine learning class. So I'm not saying much about it. Um, so here in ID3 you cannot use any kind of pruning, but in C4.5 you can do some kind of post pruning exercise after building the tree, and here also you can do some kind of post pruning in order to make the tree smaller. Okay. So as I have said, regression, when we said, that means what, these two are used only for classifications, but this card can also be used for regression. So these are the so this is some sort of comparison between different types of algorithms. So where depending on your requirement, you can use, you can choose and select which one will be important. I mean, which one makes sense for your particular application. Okay. So after this, I would just like to make one of the thing. Um, that is about this random forest. I mean, we'll not again see much detail, but okay, let me just see. Uh, so I think I've forgotten to upload it. Okay. Just 1 second. Okay, can you see? Or it has gone from the screen? Can you see? Hello, are you there or not?
Yes, ma'am.
Okay. Okay. So just to conclude, so decision tree, one decision tree was not a very good idea because uh, there is it may lead to inaccuracy or sometimes overfitting. So even though these are easy to build, and it is also very easy to use and interpret for classification problem, but it has disadvantage like any other method. So the main thing is that inaccuracy. So if your data is very similar to uh, new data for which you want to predict the class is very much like with what you have built the decision tree, so then it will work very fine, but it is not very flexible when new samples need to be classified using this decision tree. So that's why this concept of random forest came up. So from the name you can guess that it essentially tries to build a set of decision trees for the same data set. Okay, not for the same data set, by picking up data from the entire data set. So how you are choosing the data, a sample set of data in order to build a set of decision trees, that is where people do lot of experiments. So in random forest, so it's basically what is called an ensemble method. Okay, so random forest is fast kind of ensemble method. So what it does is it combines the simplicity of decision tree with flexibility, resulting in a vast improvement in the accuracy. So what it does is it creates a bootstrap data set. So what is the meaning of bootstrap data set? It means that it simply randomly selects some samples from the original data set, and by saying with replacement. So that means what? Same example can be picked up more than once. So if you have 10,000, let's say 10,000 data, so randomly you are picking up data from it, as if it's not that whatever you have picked up once, you will not be picking up again. So you can pick up the same data once again from there. So this is what is the concept of bootstrapping. So it creates a set of training data set this way using this bootstrapping method, so that the size of the data set becomes same as original. Okay, the size of the data set becomes same as the original. So if you are starting with some 10,000 data, so you may decide on, let's say, some 20 sets where each set consists of this 10,000 data with repetitions. So now what it does is create a decision tree using the bootstrap data set, but only use a here what it does, again there is a randomness over here, that's why it is called random forest. So randomly you have selected data set, similarly randomly you choose attributes at every level. Okay, so use a random subset of variables at each step. Okay, so this way you keep on building a set of decision trees. So so that is what step 3 is. Repeat from step 1 again, that is make a new bootstrap data set and build a tree considering a subset of variables at each step. So you can keep on doing it as per some kind of threshold that you can decide. So generating hundreds of decision trees. So now how do you use this set of decision trees for predicting the class for a new data? So for a new data, you pass that data through all the decision trees that you have made. So once you have, so for every decision tree, will predict a class for that new data set. So now what you do is use the majority voting, meaning that uh, whichever for that particular data, um, the majority class will become the class of this new data. Okay, so that is what is written. So a new test data comes and we want to predict its class. So take the data through all of the trees and make a count of in how many trees it given yes answer and in how many trees it given no answer. Okay. So after running through all trees in the random forest, check which option received more votes. So you can conclude the class of that new data set from this majority vote. So random forest is very simple algorithm, and but it is very useful, and it practically it has been seen that it really performs very well compared to like decision tree. So for many data set, it is a really a very good method for classification algorithm. When obviously when you use this, you use when you know that your data is not very linear. So if your data set is not linearly separable, right? So that time you use this type of decision tree algorithm, or to further improve the accuracy, you use this random forest type of algorithm. Okay. So only problem with this decision tree you can think of is like computational cost, because you are building so many decision trees, so it is computationally expensive. And there is one more problem that random forest. So I was saying that decision trees can overfit data. So that problem still exists for random forest. But overall, overall the performance is good. But another thing is that it's difficult to interpret what decision tree is giving what vote, and how you cannot interpret the result. In decision tree, you can actually analyze why a particular class you are getting for certain things. Right. So this is some kind of these are the kind of disadvantages that you have for this um, random forest kind of algorithms. Okay. So with this, we go to now some of the metrics. This also you know, but because I should go through them, so I am going through some of this metric for measuring your classification algorithm. So after knowing all these methods, somehow we need to um, say something about the performance of each of these algorithms. So how do you measure the performance of each of these algorithms? Like maybe decision tree, random forest, or whatever we have learned earlier, like KNN or naive Bayes classifier, and we'll be also looking at logistic regression very soon. So about all of this, how do you decide what is the performance of this algorithm? Or for a particular given data set, probably you have applied all the algorithms, and then how do you measure that which model is the best for a particular data set? So for that we need some kind of measure, um, some kind of measure. Now what are those measures? So all of you know those are the most measure is confusion matrix. So for this, I'm not writing anymore. I have already uploaded a document. So I'm straight away referring to that document for telling. Yes. So I'm straight away going to this because all of you possibly know all this confusion matrix. So let's look at that. So we'll be talking about this confusion matrix, and what another thing is what is called an ROC curve. So I hope all of you know about this classification matrix. Hello, do you know confusion matrix?
Yes, ma'am.
Okay, so I'm just going through it once. So this accuracy, what we typically know, this is also sometimes called recognition rate. So this is the true positive plus true negative by the positive plus negative. Similarly, we can have error rate, misclassification rate, where false positive plus false negative by positive plus negative. And sensitivity. So sensitivity is also called true positive rate or recall. So these are all synonymous actually. So whatever term you see, it means the same thing. So it's basically the proportion of the number of true positive with respect to the total number of positive. So similarly, another thing is specificity or true negative rate, meaning that out of all the negative, how many you could predict as the true negative. So these are very two important measures for overall performance of the performance of a model when you are talking about a model. So this accuracy and misclassification rates, these are measures which are some sort of gives an overall idea, and these are some this sensitivity and specificity. These are more of a kind of deep insight into the performance of the model. So precision is defined to be the number of true positive with respect to the total number of true positives and the false positives. So, and finally, in these days, this type of score, this F score is very important. So this F score is basically, you see that it uses this precision and recall. So this precision and recall, it's a kind of it's some kind of geometric mean of this precision and recall with the same weightage. So that is why you see that it is 2 into precision into recall divided by the precision plus recall. Okay. Okay, so there is another this beta where this instead of 2 actually you can have different weights for precision and recall. So I'm not going into this detail. This we can be happy with this F score. So so now let's look at, so this is the confusion matrix. So all of you are familiar too. So what we have on the y-axis is actual class, and on the x-axis we have the predicted class. So true positive is actually it is yes, and you count the number of classes where you have you could do the correct classification of positives. So true positive. So these part is the important part where it is the correct classification, and this Fn and Fp are the misclassifications. So since you know all these things, I will not talk much about it. So what I will go and so you can just go through these comments, like here there are lots of information about, I mean not information, the interpretation of each of this is given. So probably you have already done and I'm not doing it now. So what I will go to is what is, so lot of example is also given over here. So I will emphasize on the next part, which is this ROC curve. Okay. So next I'll be talking about this model selection. Okay. One thing is that this model selection can be done using statistical test of significance. So for the timing, I'm skipping this also. So this statistical test of significance is something like our linear regression, how we have estimated the beta coefficients. So similarly here we can define a metric, what is the amount of error, and on that error we do a hypothesis testing. Okay, and from the from the results we provide evidence whether our hypothesis is correct or not. So I'm not going again over here. So what I'm interested in now about this, so comparing the classifiers based on cost benefit and ROC curves. Okay, so we are comparing different types of classifiers based on the cost benefit and ROC curves. So cost and benefits in the sense risk and gains associated with the classification problem. So what is this ROC? Let's look at that. So this ROC full form is this receiver operating characteristic curves. So this is the full form of this. The receiver operating characteristic curve. So this ROC. Actually, this particular terminology came up from the field of this radar images, analysis of radar images. Okay. So basically what it does is it shows the trade-off between the true positive rate and the false positive rate. So do you remember true positive rate or recall and the false positive rate? Okay. So, so what this TPR means? So TPR, if you remember, proportion of positive tuples that are correctly labeled by the model. And what is FPR? FPR is proportion of negative tuples that are mislabeled as positive. So in certain application, it becomes very critical when whether there is cancer or no cancer. So it's very bad if there is cancer and you say no, there is no cancer, right? So that's what. So that's why this part FPR is a proportion of negative tuples that are mislabeled as positive. Here, positive in the sense cancer positive. Think of in that. Okay. So what is the trade-off between this TPR and FPR? Okay. So that means just remember this TPR is true positive with respect to positive and FPR is false positive with respect to the negative. Okay. Okay, so this FPR you can also write it in terms of like this 1 minus specificity. Okay. So since it is a trade-off, so we are looking at what kind of trade-off. So what we can do is, if you have a two-class problem, it will allow you to visualize the trade-off between the rate at which the model can accurately recognize positive cases versus the rate at which it mistakenly identifies negative cases as positive for different portions of the test set. So this is what is important for different portions of the test set. Okay. So now let's we also look at what is called the area under the curve, area under the ROC curve, which can be thought of as a measure of the accuracy of the model. Okay. So now let's look at that. First, let's look at the curve, then we will see how to plot this curve. Okay. So suppose, so this is the curve. So here on the x-axis you have the false positive rate, and here you have the true positive rate. Okay. So 0 to some 1. So obviously these values are always 0, between 0 1 and 0 1, right? So now what we plot over here is that you have a model. Okay, so let's say model 1. So in model 1, what is the value of false positive rate with respect to true positive rate? So these points are different models. Okay, so these points, these black points, these are the this corresponds to different models. Okay, so model 1, model 2, model 3, and so on. And this is based on, so these models can be many things, but in our case, let's consider this model uses a probability based classifier. So, okay, before going to that, let's look at this. So, when I will say that model 1, in the sense it's not a different model altogether, but okay, okay, I'm coming to this model part little later. So these are the some observations point where you have observed this false positive rate versus true positive rate. Okay, so now if my points are somehow, you get it in this fashion, something like this. Okay, so it means that, so this is that area under the curve. You see that this area under the curve becomes equal to 1. Okay, so the total area, because it is a 1 cross 1. So the total area under the curve is 1. So then you can say it is a very, I mean, your model, whatever model you have chosen, that model is a very good model. Good model. If area under ROC curve is near about 1. Okay. So actually you use different model parameters for getting these observations. Okay, now how do you choose those model parameters? I'm coming to it. Okay, so if you get a curve like this, that is the best possible. So we want to increase the area under this curve to be as close to 1 as possible. So suppose you get a curve like this at the 45-degree angle. So it's like, I mean, it's not really a good model. Okay, or maybe somewhere below over here, that means it is not a good model, because the area under the curve is very less. Okay, so now let's look at these observation points. How do you create such a model? Okay, so plotting an ROC curve. Okay, so plotting and ROC curve. So let's look at this. So I have a problem. I have a data set where there are 10 entries, and the class of each of these entries is like this: positive, positive, and so on, negative, positive, positive, negative. So this is the true thing. True. So now you will see one column over here which is probability. So let's say I am using a probability based classifier. So logistic regression done, but okay, I will do it soon. Probability based classifier. Just one second. Let's say I'm using a probability based classifier. So in probability based classifier, what happens is that somehow you compute a probability of, so that you remember in naive Bayes we have done, given some x equal to something, what is the probability of getting y equal to 1, right? right? So here we were computing a probability, right? And depending on whether this p is greater than 0.5, I will assign it to class 1. If probability is less than 0.5, I will assign to class 2 or whatever, class 0 and class 1. Okay. So this is, so just think about your naive Bayes classifier. Okay. Now suppose instead of having this thing as p greater than 0.5, what if I choose like 0.7 or p greater than 0.3 or so on, different types of values. Okay. So now this is the different observation points I was talking about, okay, in that graph. So all these points that we are putting in, so depending on what that p value I am choosing, probability threshold I am choosing, I am getting different TPR and FPR rates. Okay, and that I am plotting over here in the ROC curve. Okay. So now, in order to do that systematically, how will you do it? So let's say that by a model, by some classifier model, for this tuple, you have predicted this probability. So this probability is in a particular model, what probabilities you have got. Okay, and you will see that these probabilities are sorted in decreasing order of, in decreasing order. Okay, so now for each of this I have a observation in the plot. Okay, so now in this case, now you see I'll be, in order to calculate TPR and FPR, I will be requiring this true positive, false positive, true negative and false negative, right? All this 4 information will be required. So now what is written over here, just notice that if your threshold would have been this 0.90, then what will be the true positive, false positive, true negative and the false negative. Okay. So it means that only if it is less than equal to, greater than equal to 0.90, then only it's positive. So in this case, you see true positive is, it has given p, and so true positive is 1. Right. Now you look at for all the other values. So this one. Yes. And then is true. So that means for all other values, this is going to be a negative class. So among all such negatives, which has been correctly classified? So this has been correctly classified, this has been correctly classified, 3, 4 and 5. All these 5 negatives have been correctly classified. So that is why we have a true negative to be 5. Okay. Then what else is remaining? What has been? So now count which are the false negative. So false negative is this one, because actually the class is P, because since I have set my P to be greater than 0.90 for all positive class, so that means this also has become a negative now. Okay, so this is a false positive case then, false negative case then, false negative case. So this P is a false negative, this P is a false negative, this P is a false negative, and then this P is also a false negative. So there are 4. So that's why we have a 4. And is there any, so actually from here itself we can calculate. So 5 plus 4, 9 plus 1, 10. All the 10 entries are done. So there is no false positive in this case. Okay. So once we have all these entries with you, then you can calculate this TPR and FPR as TP by P and FPR as FP by N. Na. FPR is what? and FPR is what? FPR is okay. Let me write it down. TPR is true positive by positive, and FPR is FP by N. FP. Okay. So if you look at this TPR, TP is 1 out of how many positives? 1, 2, 3, 4, 5. 1 out of 5. Right. So that is why it is 0.2. And this FPR is 0. So that is 0. Right. So next what you choose is, so for this case it is P greater than 0.90 is a positive class. So next thing what you choose is probability value greater than 0.80 is a positive class. Okay. So if you do it in this fashion, let's do one more thing. One more entry, then I think it will be a clear one. So this is done. So now you see anything greater than 0.80 is a positive class, right? So that means this true positive will be what? This one and this one. So that is why it is 2. Then over here everything is negative. So true negative, then how many? 1, 2, 3, 4, 5. So again it is 5. And then false negative is how much? How many? This 1, 2, 3. So that is why it is 3. Okay, and there is no false positive, so that is 0. So this way you can calculate the 0.4 and 0. Right. I hope now you have understood what is the idea. So in this case, we are choosing that P is greater than 0.70 for positive. And this way you can see again, so these two elements are still positive if you consider this thing. So that's why it is 2. And below you can see that now false positive has become 1 because of this. Okay. This has reduced to 4 and this remains same. Right? Okay. So that means you are getting now how many points? All these 10 points you will be getting. So now these 10 points is put over here. Let me just rub off this part. Okay. Now, so these are the 10 points. So 1, 2, 3, 4, 5, 6, 7, 8. Oh no, there are some more, I think. 0.20 and 0.40. Yes. So this one, here is also a point. Okay. And this also. So 1, 2, 1, 2, 3, 4, 5, 6, 7, 8, 9, and this 10 points. Okay. So what you see, like this is the card, they have joined it in this fashion, but okay, you can create a card like this. Okay. So we can say that this is more or less fine. It's not reaching almost 1, but at least this curve is covering significant portion of this area. So we can say that this model is a good model. I mean, fixing different types of probability threshold also, you are getting a curve which covers most of this area. Okay. Okay. Okay, so this is all about the metric of ROC. So for example, over here you can see another example. So these are the two models, okay, M1 and M2. So it shows two classification models, okay. And if you see here, so you have seen two models, one is M1 and one is M2. Since M1 is covering more area, so I'll say this M1 model is the good model or better model than M2. Okay. So this will help you to decide which model you should choose. So with this, now we move on to this last topic on logistic regression. Hello, are you there?
Yes,
Are you
ma'am.
on?
Yes, ma'am.
Okay, let me just. So this last topic on logistic regression. Just 1 minute. Second, okay. So the last one is this logistic regression. Actually, logistic regression involves, in order to really understand logistic regression, it involves lots of mathematics and optimization ideas. ও দেখা যাচ্ছে না
হ্যাঁ ম্যাম ঠিক আছে।
Okay. So as I was saying, logistic regression actually involves a lot of mathematical rigor. So as usual, we are not doing it right now at the last moment. Let's just understand what really it means. Overview হয়ে গেছে কেন? Okay. So one possibility was there. Okay, let's not move into that. So let me just tell you. So what for linear regression? So one thing is that okay. So when we are talking about linear regression, so what it was like some second. Problem ঠিক আছে Okay, so what we are doing was y equal to some beta 0 plus beta 1 x. Okay, given that, I mean, we're just talking about a most simple linear regression. Okay, so then what we tried to do, we tried to find out this y cap. Um, we tried to minimize the error, assuming that there is an error over here, epsilon I. So this error we tried to minimize, right? So this epsilon I was nothing but y minus this beta 0 plus beta 1 x the whole square. And this we wanted to, the sum of all these errors we wanted to reduce. Okay, so it is over all I. And doing minimizing this function, we obtained what is the value of this beta 0 cap and beta 1 cap, and then we put all those things in this equation without this, and we found out what is my y cap, right? So that way we found, predicted the given an x, we predicted the value of y. So now the thing is that uh, what is so different in why we need logistic? Can we use that same simple linear regression for doing our classification task? Using linear regression, is it possible? What might happen? Because if you just look at this classification data set, so for example, the previous one, we are looking at age, loves soda, uh, and then whether then he likes a movie or not. Right, I just, let's consider these two things. So these are the x and this is your y. So why not? So this is a continuous variable or maybe discrete variable. And this love soda, I can obviously enumerate it as 0 and 1. Okay, or something else. So that means why not put these x values over here? Okay, in the same manner, why can't we get the things, why can't we predict this y as a 0, 1, 1, 0 and 1? So the problem is that if you even code it properly and use this type of error deduction mechanism, what will happen is that finally whatever y you get, so that you may not restrict that the range of this y is minus infinity to plus infinity, right? So if you have such a big value, then how do you interpret that as a class 0 and class 1? So maybe you can do something like a ranging kind of thing. If it is between this range, then I will say it is class 0. If it is in another range, then I will consider it to be range in another class. One more thing is that this type of things you can use in cases when I mean, when it depends a lot on this data. I mean, if the range of the data is very small thing, then probably you can use this type of the same way of linear regression for classification problem. But the problem is that it really does not reflect the true nature of this classification problem. So that is why typically linear regression is not used for classification. The main problem being mapping these real values to a 0, 1 type of thing. So that is the main problem that we don't use it. So logistic regression, when we use, so we use this logistic regression when your data is very well separated. Okay, so if you have data over here something like this and over here something like this, so when you can create a line which will separate this data into two classes, then only it makes sense using logistic regression. Okay, so otherwise what we'll use is if it is very curvy, I mean maybe there are classes, but I mean it's something like this. So here also it is very clear that there are two classes, but the separability of them is something like a nature which is a curve. Okay, so if it is a curve or somewhat spherical data, that time logistic regression will not be a good. It's not good for this type of data. But for this type of data where data is separable by a line, so this line, then logistic regression will be very good. Okay. Now, why you can possibly guess is that, so this line, equation of line is this beta 0 plus beta 1x. So while doing this logistic regression, we'll be trying to get some kind of line like this, beta 0 plus beta 1x, which actually divides it into, in case of binary classification, two class. So in case of multi-class problem, it will create a hyperplane. So something like support vector machine you can think, but support vector machine, again, for support vector machine also we wanted that data to be clearly separable, and that's why we were able to find those lines. But non-linear support vector machine is also possible, where you use a different types. I mean, instead of a line, your equation will become more complex, where it represents a curve in non-linear support vector machine. Okay, so the main thing is that if it is possible to separate the two classes with a line, then logistic regression is good for it. Okay, now how do you go about doing this logistic regression? Let's look at that. Just one second. Okay, so as you see over here in this slide, so rather than modeling the response Y directly, logistic regression models the probability that Y belongs to a particular category. Okay. So this is the probability I was talking about while explaining this ROC curve. Okay. So it just models the probability that Y belongs to a particular category. So let's say this X equal to some balance with the independent variable and Y equal to default with the some response variable with values yes and no. Okay. Now the logistic regression models the probability of what is that default being yes. Okay. So for example, the probability of default given balance can be written like this. So probability, again you see it is like your naive Bayes kind of represented. Given the balance, conditional probability. Given the balance, what is the probability that default equal to yes? So if you see this is greater than 0.5, then default is yes, otherwise no. So we can change the threshold depending on the requirement as we were looking at in the ROC curve. So now if you look at this, so this is an example. If I try to do the linear regression, what happens? So what it shows is over here is the true class, this yellow lines. Okay, for different balance, this is the class 0, and for this is the class 1. Okay, but if I try to fit a linear regression line, so this blue line corresponds to that regression line. So obviously the values that you'll be getting for a particular balance, then where you do the mapping. So these points you have to then somehow calculate this point is closer to this space, so you classify it as 0 class. And then in that case, nothing will be actually 1 class, because most of the values are more close towards this, right? So all will be classified as 1. So it's really not possible that way, at least for this data, to use this linear regression. So what is required essentially is that we want a curve like this. Okay, so a curve like this, why you see, because you see this part of the thing is mostly 0, the beginning part of it, and you see the most of its greater part of it is actually 1. So that is why this curve is like this. Okay, so they're doing a curve like this. Okay, so that means whatever probability values you get, certain beyond a certain point, so this is that point of 0.5, I will be able to put them as 0, and whatever is greater than this 0.5, I will put them as a class 1. Okay, so this is what I want to do. So this is the probability space where I'm going to get my values, right? Okay, now how do you do this modeling? So the logistic model. So for this, what we do is, say, as we have seen earlier, that we cannot, so this probability value, we cannot simply make it as beta 0 plus beta 1x, right? Because then this probability, I mean, since these values are between minus infinity to plus infinity, and probability value is only between 0 and 1, right? So you cannot do this kind of things, right, over here. So what essentially we want is, yes, so what we want, a relationship between property of x being probability of y is equal to 1 given x and x. Okay, so I want a relationship between this x and what is this probability of x. So this kind of relationship I want to build. So now, so in the previous figure we have seen this thing, this type of curve. It's a S-like curve, this blue curve. Okay, it's a S curve. So this S curve is represented by what is called a sigmoid function. So in order to map the probability values to 0 and 1, what we'll use is, we'll use a sigmoid function for mapping any value z to a value in 0, 1. So this sigmoid function has this property. You take any real value, okay, using this function, it will get mapped to either 0 or 1. So f of z equal to 1 by, so this is the sigmoid function, 1 divided by 1 plus e to the power minus z. Okay. So if you, let's say, if you take z to be, let's say, minus infinity, okay, so a very big number. So that means it is e to the power infinity, so it comes out to be 0, so it gets mapped to f of z equal to 1. So I'm talking in terms of limits. Okay, limits z tends to minus infinity. So then this function becomes, f of z becomes, what I'm saying is, if you take limits z tends to minus infinity, this will imply that f of z will become 1, because this part becomes 0, so 1 by 1 is 1. And if you talk about, if you take it to be a positive infinity, then this term is so big that this will become a 0. Okay, so that is why this maps to taken any value z, it will be mapped to a value between a 0 and 1. And that means what? Probability values are also between 0 to 1. So sigmoid function is a very good choice for this. Okay. So I hope you have understood the importance of converting a real value within this probability valid probability values of 0 to 1 in this interval. So P of x, as I said, linear regression model will not map to probability. So that's why we use what is called a logistic function. So what is this logistic function? You will find some similarities with this. So P of x is equal to e to the power beta 0 plus beta 1x divided by 1 plus e to the power beta 0 plus beta 1x. Okay. So obviously these are going to be some real numbers. And so when you, beta 0 plus beta 1x will ultimately come out to be a real number. And as a result, this P of x will get a value between 0 to 1. Okay. And this beta 0, beta 1x is an equation of straight line, right? So that means this reflects that this is the line that represents the line that separates the two different classes. Okay. So then we do some algebraic manipulation for this, and what we can do is, so if I simply do this P of x divided by 1 minus P of x, then we can get this e to the power beta 0 plus beta 1x. Okay, so just do, do some algebraic manipulation. If P of x is this, then what is 1 minus P of x? Then you substitute over here, and then you will get that P of x is 1 minus, this is going to get it as e to the power beta 0 plus beta 1x. Obviously, in a binary classification problem, if P of x is this, then 1 minus P of x is that other class, right? So now this particular term is important term that is called in logistic model as the odds ratio. So odds ratio is basically a ratio of, if you see, for one, it is a kind of ratio, a relative, what should I say? It's a proportion between the positive class and the negative class. That's that way, if you can think of it. So that's why it is called the odds ratio. So now this particular thing takes values from 0 to infinity. So now what we do is we take log on both sides. So what we do is log of P of x divided by 1 minus P of x, it becomes, then you actually get this beta 0 plus beta 1x like this. Okay. So this is this particular thing, when we take a log, then it is called a logit model. Logit model. So logistic regression model has logit. So this particular expression is called logit. So that is linear with x. So this particular thing, log of the odds ratio, is actually linear because that can be represented as beta 0 plus beta 1 of x. Okay. So we started with what is the relationship between this probability of x and this x. So this is the relationship that we come up right now. Okay. Okay. So in linear regression model, so actually how it is differing with the linear regression model. So that's what I've just jotted it down. So in linear regression model, beta 1 gives the average change in y associated with a 1 unit increase in x. But here what it means, here what happens is in a logistic regression model, increasing x by 1 unit changes this log odds by beta 1 because it is log over here. it changes the log odds by beta 1, or equivalently you can say it multiplies the odds by e to the power beta 1. So this is the difference with this linear regression. So now the next point is that how do you, so that means what? You can see here I have to estimate these parameters, then beta 0 and beta 1x, meaning that somehow I need to find out what is this beta 0 cap and beta 1 cap, just like our linear regression. So how do you go about finding? What is your objective function over here? Okay. So for this, what we use is what is called a maximum likelihood function. Again, this is where you need your optimization theory. You must be very thorough with this optimization theory. But since you do not have the background, I'm just going through it very superficial way. So we use this maximum likelihood to fit a logistic regression model. So whenever I'm saying fitting means basically finding parameters. Finding parameters, then beta 0, beta 1. Best fit we want. Okay. So we seek estimates, so that's what I've written. We seek estimates for beta 0 and beta 1 such that the predicted probability p cap xi of default for each individual. So when I mean this default, this default means what we say is we say that first we are probability of x. Now what is this x? And then another one is 1 minus p of x, right? So this x, this I'm calling it to be a default. Okay. So this is one class I'm considering it to be a default class. And 1 minus p of x is the other class. Okay. So that's why I'm using this term default. So we seek estimates for beta 0, beta 1 such that the predicted probability p of xi of default for each individual using this formula p of x. So ultimately, if you get beta 0, beta 1, what you have to do, substitute over in this expression p of x equal to e to the power beta 0 plus beta 1x divided by 1 plus e to the power beta 0 plus beta 1x, and you will get the probability values. Right. So using this corresponds as closely as possible to the individual's observed default status. Meaning this probability value I should be, it should be, if it is default class is yes, then probability value should be such that it is greater than 0.5 and I will be able to predict it as class, the default class. So that is the idea. So it corresponds as closely as possible to the individual's observed default status. Now, how do you model? How do you represent this corresponds as closely as possible? How will you define as close as possible? So that is where maximum likelihood comes into picture. So beta should be such that plugging this estimate into the model for p of x yields a number close to 1 for all individuals who defaulted, and the number close to 0 for all individuals who did not. Okay. So that is what I said in the previous statement. So how this is modeled then? So this is also called a loss function also. Maybe you have seen in machine learning loss function. So this likelihood function is defined like this. Typically it is denoted with this L. L of beta 0, beta 1. It's basically the product of for all i's. So you see here for all i's. So this phi is product. Okay. So now for all I, where I equal to 1, you take this p of x, and for all j, all I, I dashed, all I dashed, yi dashed equal to 0, for them you take the probability 1 minus p of xi dashed. So what do you understand from this? That means basically I am considering in whichever entry we have a 1. I take the probability of that xi and multiply. So we are sort of maximizing this term. We want to maximize this term. So we maximize the log likelihood function using what is called an gradient ascent function, as it is a maximization problem. Okay, since I want, so what will happen is that if you see, if your yi is 1, so then p of xi part will be there. If your yi is 0, then this 1 minus pxi part will be there. Not both the part will be there. Either this part, left hand side part will be there, or the other part will be there. And what we are trying to do is we are multiplying all of them. Okay, so thereby we are trying to, so that value I want as big as possible. Okay, so that is why this likelihood function that we try to optimize, we want to maximize this, and this log likelihood that we are using because it gives us some kind of advantage in doing the maths for maximization functions. So I am leaving it over here. I'm not going into how really we do the maximization because it will require lots of maths now. So after that, what we need is making the predictions. So as I said, given x, so if you solve this thing, if you solve this likelihood function, so from supplying this p of x values and p of 1 minus px values and things like that, ultimately you will be getting the values of beta 0 and beta 1. Okay, so that means you can now substitute it in for a given x. If you want to classify given x and obtain beta cap from maximum log likelihood function, we can simply use this function p of x equal to this to predict the class probability for yes. And if probability is greater than 0.5, it is a class yes. If the class is no, meaning whatever, default class and not default class. So we can also compute the probability for no and apply the same threshold. So note that for a given x, we might get equal probability. Okay, thus it may belong to either of the class. So what does it mean? It means it is on this decision boundary. So if you get, for example, you from the data set available, you have got a classification. So new data comes and you get a value which is exactly 0.5. So for this, it is on the decision boundary. So it can either go to this class or this class. So that you have to leave it to the user what he or she wants to do. Okay, so this is all about this logistic regression. We have done it very superficially, but okay, at least we should have the idea of logistic regression. So that's it we have for the timing. I hope I have covered everything. Let me just check once. I have made a list of things. Yes, I think I have covered. Yes. Oh no, one more thing I have to tell. Sorry. I just forgot to tell you about k-means. So this is about logistic regression, right? This is all I have about logistic regression. So k-means all of you know. So I don't think it is really good. I will upload this slide also. And k-means all of you know, but just from my side, I'm just telling it once. So all that we have done so far is, so this is also a handwritten note. So far what we have done is all supervised machine learning for classification problem. Supervised classification we have seen. So, but there could be unsupervised classification problem. Unsupervised means where data is not labeled. So there is no specific class given for the entries. So it's kind of, we want to find natural cluster in the data set. Hello, are you with me? Hello.
Yes, ma'am.
Hello.
Yes, ma'am.
Okay. Fine. So so for that, so when the data set is not labeled, so then we say sort of we want to find the natural clustering in the data. So natural class in the data. So in order to that, what we use is what is called k-means clustering. So I think you have studied this, but just to do a kind of recap. So this is a technique to partition n observations into k clusters. So unsupervised classification, typically we call clustering methods. Okay. So where the number of classes obviously is going to be less than equal to n, in which each observation belongs to cluster with the nearest mean. So in k-means algorithm, I will classify a point which is closer to its mean as belonging to that cluster. So there is a concept of cluster mean value, and any point which is nearer to a particular cluster head or cluster mean, I say that particular data point belongs to that cluster. So one of the simplest unsupervised algorithm, so where data is not labeled into classes. So it works well, you know, for all distance metric. So when mean is defined, so we need to use a distance metric, the distance between two data points. So this that could very well be Euclidean distance or any other distance, Manhattan distance, or there are many possible types of distance, Mohalanovic distance, Edik distance, different types of distances we can have. But typically we will see over here is what is called the Euclidean distance between 2 points is the measure that you try to optimize in k-means algorithm. So how many groups or clusters are not known? So this is some form of categorization or classification without any supervision. So k-means clustering again can be thought of as an optimization problem. So what we are trying to optimize over here, that is the distance of each of the points that belongs to a cluster, sum of the distances of points that belong to a cluster to its cluster mean. So that distances, we are sum of all these distances we are trying to minimize. So more formally, what we can say is that given n observation x1 to xn, k means partition n observations into k sets. Okay, so the sets are like S1, S2 up to Sk, such that, or these are the clusters actually, S1, S2, Sk are k clusters, such that it minimizes what is called the within cluster sum of squares. Within cluster sum of squares. In short, it is written as WCSS. So what is the meaning of within cluster sum of squares? That is what I was telling you that time. So let's say mu I is the mean of points in cluster Si. In cluster Si, mu I is the mean of points. So now for every other data point x minus, so the distance of x with mu, so that I'm writing as distance of x minus mu I squared. Okay. So basically what I want to write is distance between x and mu I. So that distance I'm squaring it because of that getting negative, positive and things like that. So that's why I'm squaring it. So this I need to use a double summation because x belongs to this. Because x belongs to this cluster I. So that means it is the within cluster sum. So this sum corresponds to this within cluster sum of squares from the cluster mean point, and then over all clusters you sum them. Okay. So that's why you have a double summation. So that means if you just try to look at an example, what it means is, suppose these are the points in one cluster and these are the points in another cluster. Okay, so that means the mean is going to be somewhere over here for this particular thing, and for this one the mean is going to be somewhere over here. So what I am trying to do is calculate. So this is your mean, right? So these are the means. So distance from each of these points. So this is that um, within cluster distance. So all these di's. So this is this part of it. Then for here also all these di's. Okay. And then whatever di you have got, then sum them. All the sum di's you have to sum for every cluster. So this is this. So, and we want to minimize it. So this minimization function min s. So now for this also we can prove that k-means algorithm is a very simple algorithm, that we can show that it gives a, it does indeed minimizes this. Okay. So here one thing you have to notice is finding the number of clusters is difficult. So we typically start with 2 cluster heads randomly, and then the quality of result depends on this initial choices. So the algorithm is what? Randomly choose 2 points as cluster heads or centers, assuming that we have 2 clusters in the beginning. So if you are not happy with the result, if you have to keep on increasing the number of clusters and see whether that within cluster distance is reduced. Okay, whether this within cluster sum of squares reduces. Now compute the distance and group the cluster, group the closest ones. Okay, so that means for every point I am seeing what is the distance between head 1 and head 2. If that point is closer to head 1, then I assign that particular point to head 1. So then after finishing all the points, again we do new mean and repeat step 2. So we will keep on doing it until and unless we are happy. If change in mean is negligible or there is no reassignment of points to new cluster, then stop the process. So what might happen in first iteration, a particular point may be in closer to one cluster. So in the next iteration, because many other points have come into a particular cluster, so the mean will be shifted. So once that mean is shifted, for all the points, again we recalculate the distances. So as a result, it may happen that point may no longer be closest to the earlier cluster, but to some other cluster head. So that's why there may be changes in assignment of each of these data points during the process of the algorithm. So we stop when we see there is no reassignment, or if we see that the cluster heads are not really moving much from its previous iteration. So issues to be considered, dimension of data does not matter, but we need to specify the number of clusters. No label given, but at the end we categorize the data into classes of cluster. So how do you determine the number of clusters k? So k is not like a parameter. So this is also called a non-parametric thing. So k means is non-parametric. Okay. So this ELBO method we earlier also talked about it. How do you determine what is the ideal number of clusters? So what this ELBO method does is it looks at percentage of variance explained as a function of number of clusters. So the point where there are marginal decrease and forms a plateau, that is an indicator of optimal number of clusters. So if you look at this, so what we can do, suppose you are applying for k-means algorithm, you are trying to identify what is the true value, ideal value of K. So what he said is start with 2 clusters. So with 2 clusters, you check what is the total this within cluster sum squares value that you have got. So you plot a point over here. Then slowly we increase the number of clusters and see what is the kind of value you are getting. Okay, so if you increase the number of clusters, definitely the total WCSS is going to decrease because you are getting more cluster heads, right? So, so this is what it looks like, an elbow. It's like a hand, right? Arm. And this is the point of your elbow. So it is a point where after which it becomes more or less like a straight line. Okay, so maybe in this picture, not really this one is an elbow. Probably over here you can think of it as an elbow. So maybe after that, even if you increase the number of clusters, there is not much significant change in the amount of WCSS values. Okay, so that point is typically considered as the ideal number of clusters. So disadvantages of K means it can converge to a local minima. Obviously, that problem is still there due to initial choice of cluster heads. Depending on your choice, it may run for long. Okay. Another thing is that if the clusters are not spherical, then K means can fail to identify the correct number of clusters. So what is the meaning of spherical? So this is what is spherical. Sphere, this is also sphere. So if it is clearly separable, again that thing comes out. So then K means is very good. Okay. So basically in this case, what is this type of data? Once you get your head, in next iteration onwards, the head will not move much in this type of data set. But if you have this non-spherical data, so you see here, this is one portion and this is one portion. It's like, it's like this. One is within what? It's not separable actually. You need a curve to separate them. Okay. Then it is difficult for K-means because this one, an element if you have over here, this may get assigned to this also, this may get assigned to this also. Okay. So difficult for K-means if it is a non-spherical data. Okay, so here I've given one example. I think that you can see later. So there are just 4 points. So you can see the natural cluster. AB is cluster 1, CD is cluster 2. So these are the values of them. Okay, so initially I have chosen 2 cluster heads to be 1, 1 and 2, 1. So this you can choose it either from the data set itself or something else also. Typically we choose from the data set. So 1, 1 and 2, 1. So you will see this A and B. So initially I've chosen the cluster heads from the same, right? So then you compute the distance of all 4 points from 2 centers C1 and C2. So C1, from C1 this gives the distance of ABCD, and from C2 this gives the distance of ABCD, right? Now since for C, C is more closer to C2, right? So that's why I assign C to C2, and for D we assign it to C2, right? So this is the situation now. C1 is assigned to A and all 3 are assigned to C2. Okay, so now what you do is again you recompute the centroids. So C2 centroid now will change. Okay, it will become, this is the centroid. C1 centroid remains same. Now again with respect to these 2 centers, C1 and C2, now again you calculate all these distances and reassign the points to different clusters. Okay, so this way you keep on doing until and unless there is no more change, and at the end you'll be getting the through clusters. Okay. So this is all. I will upload this slide also in case I forget. Just remind me. This K means and K means I think I have uploaded. I don't remember. Okay, let's see. So study well and all the best wishes. Anything else if you want, you can contact me. And that's it. Okay.
Okay, ma'am.
Okay.
Thank you.
Okay, I'm just leaving because I have another class now.
Okay, ma'am. সবাই অ্যাটেন্ডেন্স নেওয়ার জন্য বসে আছে। অ্যাটেন্ডেন্স দিয়ে কি করবে? বেরিয়ে যাচ্ছে।